All right. Hello, everybody. At least hello, Brandon. It's time for part 6 of the SC30 Reloaded assembly build. SC30 Reloaded is the proper project name for this, as I've been reminded of recently. I have my headset here hanging from my neck. I think that my voice should be coming through the mic now. The mic on this headset. That's what it looks like on the audio mixer anyways. Maybe if I can... Oh, it's much clearer, really? Oh, that's great. Maybe I can just... let me bring the Logitech webcam microphone down to 0, just so that we don't get any noise from that. Yeah, the equalizer things here suggest that it's only being picked up by this mic. So hopefully that will cause less, or give us less noise doing this. All right. So let's see here. Let's bring up some tools. So a couple of things. This video will, at least the first half of it, is probably gonna be fixing some of my mistakes from previous videos. I have at least 2 mistakes, a little bit of a cleanup work, and probably some more testing required before we can move on to the final assembly step. So first of all, I guess a quick status update. So if let me go back to the browser real quickly. See here. Bringing up Google Photos. I probably tried turning on the extractor. Yeah, I should turn on the extractor. I'll do that in a minute. Let me just see here. I need to change the window here to photo. There we go. All right. So after the stream last night, I thought I'd take the first step of cleaning up the board a bit, since we were done with the SMD component assembly. So there was a lot of flux residue, especially from the solder paste. So I dropped it in a bath of 99% ISO. IPA, sorry, ISO, what's that? IPA, and let it soak for an hour. And then I rinsed it, then I scrubbed it down with a dishwashing brush, as well as my trusty old toothbrush. And then I rinsed it in distilled water. So after that, the board looked something like this, and it looked pretty nice and clean. However, if we look at what it looks like today, we have a whole bunch of pretty ugly residue making a return here, and this is something I've seen happen before, and Brandon rightly called out. I sent him a picture earlier today that this is clearly the IPA reacting with the flux and creating this sort of salt-like white residue. And I don't think this is harmful in any way. I don't think it's conductive, but it looks horrible. So I'll definitely have another go at cleaning this up. And let's see if we bring up a little plastic tool so we don't scratch the board. So yeah, look at that. It's like this salty. This is a little bit more. This is a little bit more viscous right over here. But yeah, the white stuff is kind of this salty residue. And I think so with IPA you get rid of it for temporarily. You can kind of wipe it off. Oh, wait a minute, that looks like a little bridge there. I should probably clean that up. So IPA will take care of some of it, and I think also some more distilled water. I also like to use my gentle dishwasher liquid to get a little bit of a nicer finish. Yeah, because this does not look great. We want a nice and clean board. Yeah. So let's see if that's actually a bridge right there. I'm talking about. Let's see here. Um, this right here looks like a solder bridge. Um, yeah, we don't have. There's no continuity there, so I guess this is just some dirt. Seems okay. Actually, let's angle this down a little bit so that you can all get a view on my desk again, like so, perhaps. So a little bit of cleanup work will be required here. I will not do that right now. But I think lesson learned here is after you've done. So again, I don't have a um, ultrasonic cleaner, so I can't really do this the right way. But yeah, if you need to clean up after flux, I think IPA bath is correct, but then you need to really thoroughly rinse it with distilled water afterwards, like really, really thoroughly. Perhaps let it bathe for a while and then scrub it some more, and then really dry off. I think Brandon, you mentioned that you're using like a fan to really blow all the liquid off before it dries on top of the board. Go with this anti-static brush. Just brush this stuff away. So yeah, there we go. Okay, so let's turn on the fume extractor. See if Brandon, you tell me. So now it's running, and now I'm talking again. How is the noise cancelling working? I can barely hear it. Okay, so you can barely hear the fan, but you can hear my voice, right? So yeah, Brandon is saying, when I do it with a fan, I wipe off the residue when it starts to come out from under the IC, since it's not pure IPA or distilled water, and whatever is in it leaves streaks. Yes. Yeah, that sounds about right. Yeah. It's funny. Way back, one of the first, or pretty much the first real big soldering job I ever, or kind of this kind of repair tinkering job I tried was a PC Engine Duo. And after doing some work on it, I did what, and there was a lot of flux residue on the back of the board when I got it. I mean, out of the factory, right, when it was manufactured in 1990 or whatever. Tried to clean that off with IPA. Looked okay when it was wet, but then when it dried up, it was like covered in white, faulty residue. And I got shocked almost, and I started asking around online what was going on with that. I think they asked on Reddit. And I was told that, yeah, that's just the residue you get when you combine flux and alcohol. So it's a thing. All right. So on to my mistakes. I made two pretty big, or big, two mistakes in the last stream. Now, I think folks who actually know about this stuff, if they watched my previous stream or the two previous streams, they might have been screaming at the camera or at the screen, telling me like I'm making such a huge mistake. but I realized it just today. So the first mistake, I was told by Bolly himself. I posted a picture of this board on the Tinker Different Discord server, and Bolly himself responded and said, please swap out the ASC and SCSI chips. Otherwise, it looks good. So, the second part was great. I'm really happy that he thought it looked good. That's great words coming from him. But when I looked closer at it, I did realize that, yes, I had the SCSI chip, which is right here. Oh, this is the spot for the SCSI chip. This is where I put the Hitachi IC. Turns out that this Hitachi IC is actually the ASC chip, which is a proprietary Apple chip, which I guess you could realize if you see the copyright Apple on there. I should have realized perhaps. And then that this chip, the NCR chip, 53C80, this is actually the SCSI chip. So these two ICs need to be swapped out. I'll do that in a minute. Hopefully, so since we use the solder paste, low temperature solder paste for this, may be easy, we'll see. But it may be a huge pain because these caps sit just next to it, and then we have the fuse on the other side, which is really fragile as we've established. And then we also have the cap here, cap, other big chips nearby, small chips nearby. See, I'll do that in a minute. But if you recall, I did some half-assed attempt at measuring whether these resistor packs were actually working or not. And I kind of said something in passing that I should really look at the data sheets for this. But I won't. And that was a huge mistake. If I had looked at the data sheets, I would have realized something. And I don't know if you all noticed it. Namely, this chip right here is wrong. This is the wrong chip. Now, I found that out thanks to the data sheets. But if I had looked closer at the BOM, I would have also been able to spot it. So if we look at our P8, switch over to sheet here, these 1K ohm, part number 4816P 002 or 002-102. What does it say here? 4816P 102. And at the time, I didn't know what this 1 signified. But what you can do in these situations, and this is easy because this is a new chip that I bought, which means that we can head straight on to DigiKey where I placed this order for these parts, and find the chip that I ordered, right here, this resistor array. And then let's compare it with this other resistor array, which is the chip that sits just below this 221. This is a learning experience for me, so please bear with me. So if you now open up this data sheet, which DigiKey always provides very helpfully. And by the way, these two chips have the exact same data sheet. It's the 4800P series. So these two are identical. They just have different specs. So looking at this, so I cannot make sense of absolutely everything on here, since I'm just an amateur. But what you can tell is, it says here, how to order. That's very helpful. It's good to read the instructions. So we have the model number 48. We have the pin number, 16 pins. So 16 means 16 pins, which is what we need here, 8 on each side. -1, electrical configuration. 1 or 4 means isolated. 2 means bust, and 3 means dual terminator. What we need here, so what I ordered, let's start with that. So what I ordered here was 1. Then let's look at the next page. Here, this is the specification of for how this IC works. So we look at the isolated type here. We have the bust on the side, and then dual terminator over here. Isolated. So if you look here, it means that pin 1 is effectively connected to pin 16 with a resistor, and so forth until 8 and 9, right? So it's just straight over. You will have resistance. It's like 8 resistors in a row, right? Let's test that, just so that we can kind of validate. Sorry. I forgot to switch over. Okay, let me start over. I was looking. Here we go. Here's the data sheet, right? I was looking. By the way, so I was looking at this. Oh yeah, you saw that, and then I show you this, and then we went over the data sheet. Here's the how to order section, right? The model series, 16 pins, right? -1. Isolated, bust. So 1 means isolated, 2 means bust. Here are the isolated pin breakdown. So pin 1 should be connected to pin 16 through a resistor, which means we should get 1 k ohm resistance. And let's see if there is a good way to. My multimeter has a pretty faint screen, so I don't know if I can show you the multimeter. So something like this. So here you can at least see what's on the multimeter screen somehow. Oh. Keep pulling the leads. Here we go. Okay. Right. So if you measure from pin 1, which is the pin next. Oh, sorry, over here. Next to the mark there. Measure over there. We get 0.993 kilo ohms. That's correct. What if we measure between pin 1 and pin 15? There's no resistance. There's no connection. But if we measure 2 and 15, we have the 1 kilo ohms there again. 0.99, and so forth down the line, right? So that's how we know that this is a good resistor pack. Very happy resistor pack. Here we go. Okay, all the pins are good. So you know that it works. Now, let's compare with this down here, right? So this is the bust resistors. Here we go. So the bust resistors, as you can see, pin 16 has no resistance, whereas pin 1 through 15 are connected in a, I don't know what this is called, with a proper term, it's like a matrix. So these resistors are all effectively connected directly to, well, they're connected together. So if you measure from pin 16 to any of the other pins, you'll get the resistance, right? Whereas if you measure between any of the other pins, you'll get double resistance, effectively. So let's test that real quickly. So pin 16. So this is rated for 220 ohms, I believe. So let's test between pin 16 and pin 15. There you go, 221.2 ohms. Works as specified. Works as specified. Let's just do a spot check. Oops. 220. 221. That's a perfectly functional chip. It means, however, that this board is spec'd for a bus resistor pack, and I installed the other type, the isolated one. That's not good. So this chip should not be here. Now, unfortunately, I looked in my stash and I don't have a 1 kilo ohm bus resistor pack. So I'm gonna have to put back in the other 220 ohm resistor pack. I don't think that will be a huge disaster. I think that it should work anyways. That's what I've been told anyways. At least for the chime test, it should be all right. So ironically, this is what I actually put in first and then took off, and now it's going in again. So that's kind of funny, I think. So back to the original thing I was trying to do. I was trying to determine whether these 112S0300 chips were working. And I couldn't find, I don't think these resistor packs are not manufactured anymore. I could not find the data sheets for this particular kind. But now at least we know that it's likely going to be either a bus or an isolated resistor pack. So we can at least test what this is, right? So if we can just, if we try this chip for instance, if we test from the pin 16 to pin 1, oh, that's not good. Let's try again. So we have 22 ohms there. How about if we move it 1 pin over to pin 2? Nothing. No connection. There we go. 22 ohms again. Tells us that this is an isolated resistor pack and that it works. So that's great. So I'm not going to test all of these on camera, but I didn't spot check them all and they seem to be working. So these are seemingly good resistor packs. I think we had one more type down here. This one. See what type this is. Between pin 16, pin 1. Oh, slipping and sliding. This is looks like 1 kilo ohm. What if you go to the one to the side there? Okay, that's not what we should be doing. We should be testing this one. This one. There we go. So this is a bust resistor pack rated for 1 kilo ohm. So it's the same as what this should be. This should have been. So yeah, that was a mistake, and now I know more about resistor packs. So let's do a switcheroo here. Time to break out the hot air. Temperature, bring it back to 350. Have the tweezers ready. Apply heat. slides right out. All right. So we have a perfectly fine but not really what we need chip right there. All right. So let's bring out this 220 ohm bus style. Put some water onto my sponge. So, by the way, I did find my new sponges. This is a very nice and clean sponge. So let's start by cleaning up these pads here. We don't really want to reuse that. We should start over. A lot of glare. Lots of glare. Seems alright. Turn down. No, it doesn't help. It's just the glare from this LED here. Maybe turn down the LED a little bit. Clean up this pad. Nice and clean. So let's use the soldering iron technique. 350 degrees Celsius. Which patch? It's 10. Just do this one. There you go. It's weird. It's just the picture's just so blown out. Just very blown out. I don't know what. No good. Maybe because it's dark outside. Probably need better studio lighting. That's better. Okay. All right. Chip is coming in. Coming in for docking. Let's live dangerously and use our fingers. Compensate exposure as you adjust the light. The best way to make it work is probably what you just did. Turn the LED to the very lowest level. Yeah, maybe. Okay, so let's see what happens. Now this is where the microscope's LED is off, and my desk light LED is on full doesn't really adjust back up. Not off, just to the minimum. Okay. Yeah. Maybe I'll turn off the ceiling light. Anyway, let's solder this on. Where are we? There it is. You could try moving the microscope farther from the board. Yeah, the problem is that I kind of want this much reach so that I can actually get to all spots on the board I'm working on. You know, I need to be able to reach the middle. So I don't really have leeway with this very cheap microscope. Probably as good as it's gonna get with this equipment. Anyway, can you put something under it to lift up? Well, I can't because I've super glued it onto this board, this stand here. I did that in the second episode because the suction cup didn't really work. So let's try this without flux and see if we can get it on. Yeah, so Brandon, if you watch my second episode, you'll see when I super glued it. Okay. So we have a bridge here. We can take off. Bridge is gone. All right. Those joints look pretty good. Yeah, I think it's just because I have less daylight right now. It's pretty dark, so I'm not. When I'm filming in daylight, I think I get a much better picture on the close-up here. So anyway, let me just demonstrate. Switch back to my face. Hello. So what I this is what it looks like. Right. So it came with this what do you call that? Like a foot. And you're supposed to use the suction cup to put it on this. So this is what keeps it stabilized, right? You could theoretically put the suction cup on your desk, etc. But it wasn't sturdy enough for filming, right? It kept falling over. Yeah, so I mean I could, but then I won't have, you know, what's my workspace then? I don't know. Okay. Yeah, maybe I can experiment with that later. This chip aside. Anyway, so now we have at least a more appropriate resistor pack installed there. Yeah, I'll play it later. So the next, this is what I'm dreading. Let's see how painful this is going to be, but I need to swap UE10 and UI12 around. And let's actually, before we do that, let's just validate against the bomb that we're doing the right thing now. Here we go. So UE10. UE10 is the Apple ASC. Yes, we know that. And part number is either 344SO0063-A or VLSI VC5007-0001. Let's compare that then with the Hitachi chip. 344S0063A. 344S0063A. So yeah, this is clearly the ASC chip. It should not be in this SCSI slot. And the opposite. So yeah, sorry about the upside down picture, but the SCSI chip on UE10, UE10. Wait a minute, sorry. No, the SCSI is UI12. UI12. SCSI controller chip. It's the 53C80. So this is not an Apple proprietary part. This is a standard SCSI controller IC 63C80. 53 rather. 53C80. 53C80. There we go. Now we know for certain that these two chips are on the wrong way. Let's bring out the hot air. So I'm a bit torn here. I may want to. I'm gonna see if it's how nice it will look if I just use the hot air, heated up both of them fairly, evenly. They start to melt, and I just swap them over, and see if the whatever solder kind of remains is going to be enough. This will be very interesting to see if this is actually gonna work. So I'm gonna hold the camera on the NCR chip, but I'm gonna kind of go back and forth between that and the Hitachi chip. This should theoretically be fairly quick because this is the solder paste. There we go, came up. Whoops. Put it there in the middle somewhere. Ew, look at that. Okay, that's pretty gross. I need to clean that up. Okay, oh, sorry. So here, this chip is coming off. Okay, so I really need to clean this up probably before I do anything else. Let's see if we can get some alcohol on there without, let's see here, I need a toothbrush. Okay. Well, let's see what happens now. So we need to put the Hitachi chip should go on here. Yeah, this is probably not gonna be very nice, but Hitachi chip goes there. And CR chips goes here. Okay, so let's see what happens when we start melting this. To put camera on here. There we go. So this is probably not advisable. I bet I should have put new solder on here, but let's see if we can get away with this. So at a glance, it looks alright. Let's go back to this chip. Put it in that orientation. Okay, so the solder is definitely melting there. Oh. Let's have a quick look with the loop. Yeah, so the chips are definitely on there, but the joints don't look super nice. So I think at the very least we need to apply some iron. Plus the little bit of spillage over here. This is solder residue that came off when we pushed this chip to the side there. So for starters, let's just apply some heat around here. See? So yeah, there is solder there. That's good. Do a little drag action. that. Okay, let's check the joints on the ASC chip. Looks okay. By the way, I should mention also, I think Brandon, in an earlier stream, you talked about this form factor of a chip, and we were talking about sockets for it, and I kind of said I don't know what this package is called, this form factor is called, and actually, if you look in the BOM, it very helpfully tells you right here that this is a PLCC package, right? This is the package. This is the chip that's kind of defined by these J-shaped pins, right? And they are indeed commonly used PLCC sockets that you can just push these chips straight in. You don't have to solder them on a board like this, and yeah, that is much preferable to this kind of painful soldering work. But Apple, in their indefinite, I can't speak today, endless wisdom, decided to put them, PLCC, that's what it's called, have them soldered onto the board instead, and it's just a pain to do every time. So let's refresh these joints as well. Infinite, yeah, thank you. Infinite wisdom. Oops. This is where we have these stupid caps here, kind of in the way. This is why you really wanted to do this before you got the caps on. Oh, nice. We're getting the first spam messages in this chat. I feel honored. Hello, spammer. All right. So we touched up all of the pins. It looks acceptable, but I'll probably, yeah, they're kind of, the joints are kind of dull though. I'm not super happy with how they look. But anyways, as I think I mentioned in the past, this NCR chip, this SCSI controller, is probably the chip that's in the worst shape out of all of the donor chips. It has pretty crusty legs because it sat next to these three caps, or it sits next to these three caps, so it had leaked terribly. So yeah, if SCSI doesn't work, then yeah, we'll have to look for alternatives. But this is a standard chip that's available for purchase. Well, new old stock or used. I don't think they're made anymore. But unlike these Apple proprietary chips, these are actually possible, or more easy to procure. So anyway, at least the chips are in the right spots now. That's an improvement. Let's clean up this gunk here. Beautiful. So I think this is a good time to switch over. Actually, look at that. Let's use some wick. The crappy wick. See if we can. Crappy wick is still crappy. All right. I think this is a good time to install the very last component that was salvaged. This is a nice little crystal. I'm pretty sure crystals are not polarized, and it has a little bit of stray solder on the leg there. I should probably clean that up. Do that just see if we can actually. This is heat tolerant, heat resistant mat, so it should be good to do just like something like so. There we go. Oh, they're still on there. I think that's good enough. It's still kind of this weird little wedge sticking out on the side. Okay, looks better. Yeah, so let's install the very last salvaged component, which is, I think, J11 right there. Let's double check against the bomb. J11. there it is. Oh no, that's speak of course the jumper. Sorry, Y3. Jeez, Y3. That's what we're looking for. Y3. Crystal, 16.9344 megahertz. And this came right off there. So I think there should be 2 crystals of this form factor on this board. The other one is Y1 over here. There's Y1, and that was horribly battery bombed, of course, because it sits next to the battery here. So that one we don't have, but I have a new one of those. So rather we didn't get it out of the donor board. I wonder what Y2 is. What is? Let's see. Y2. It's also an oscillator, but it's different package, I'm pretty sure. Main logic board clock signal. So what is that, like an IC? Y2? Yeah, I'm not sure. We'll find it soon enough. So anyway, we should put this, install this in Y3. Jumper. What's that, by the way? Is this? Looks like some gunk that we should get rid of. Better. That might have been a breach. There it is. So yeah, I guess we should celebrate our first through-hole component. And when I solder through-hole components, let's see here. I have a trick. Let me get some equipment. I like to use blue tack. Just some standard knockoff blue tack. The nice thing about using this stuff is just pull off a little piece like so. Can mold it into a, can stretch it out a little bit more, and then kind of put it on top of the component you want to solder like so that it's held on. And then you are free to solder that on. I don't know if you can find it. Ah, there it is. We're not getting heat onto there. Nope, still not working. Still not working. Okay. That's better. See if we can get heat onto this pin now. Here we go. Now it's in there. And we can take the blue tack off. Oops. There's the crystal. So yeah, it's a little bit skewed to the side. So this might be painful. I usually try and fix it. So this might be painful because it's gonna be getting a lot of heat in there, probably, or it's gonna heat up very quickly. Hurt my fingers, but I like to kind of adjust components. They're nice and even. So what I'm doing is I'm just holding onto the component with my fingers and heating it up and then pulling it out a little bit. And I think with these crystals you want it to have a little bit of leeway so you can be kind of pushed down towards the board like so, otherwise it might snap off. It has this awkward form factor. Alright, so this little bin is now empty. We have, except for the stray pad there, which hopefully comes from the donor board. So we should probably install the other crystal, which I have baggies here. So let's see if we can pull out some parts that we need. So we want, let's see here, crystals. From Mauser. Pretty sure these are the right crystals, otherwise they wouldn't be in this box, but I'm not sure how to read. It doesn't really say anything about the spec. Look at the bomb. Y1. Oh, Y1. So yeah, it's actually the real-time clock crystal, so I guess it's not 100% required right now. But let's get it in there anyways. It's kind of weird. I'm not sure. I do like to, double check that I'm getting the right part in the right spot. So I'm not sure what on here tells me that this is a 32 megahertz or 33 megahertz crystal. So I may want to just drop into Mauser and see if we can validate that. I mean, this is not a hard part to swap out later, but it's good to be safe. Better safe than sorry. So let's go to Mauser, pop in the part number. So this is what 695. What? Weird. 95 CFS CFS 20632 20632 768D 768 ZDB. Copy that just in case I got it a little bit wrong. There we go. There's one in stock. Oh yeah, so this is the 33 kilohertz crystal. No, kilohertz. Wait. Oh, kilohertz. Okay, it's not megahertz. Kilohertz. Yeah. Okay, so I guess we have the right part. These are a lot smaller than the original parts. Whoops. Just rolling, rolling. Here she is. Actually, just for, never mind. I think I have a 33 kilohertz crystal on the 2SI board, the donor 2SI board, so I could steal one from there for a little bit better authenticity, but let's go with this new part. So we're gonna just pop it in there. This is a lot smaller than the original part. Put the blue tack on there. There's a blue tack held in place. Flip it over. Actually, there we go. So I still want to leave a little bit of leg room on top so that we can bend it over. Actually, that's probably what I want to do. I think it's better if we make sure that we are able to bend this crystal on the side. So we put it like so. There we go. This should allow us the ability to always bend it over if needed. So there are the legs. There we go. Nice. Crystal is on. I think I should cut those legs. Definitely long enough that they may kind of end up touching those two capacitors. Maybe they are all connected. Oh yeah, it looks like they're connected anyways. Test that. Yep. Yep, they are connected there. Yeah, sure, we can cut them. For the sake of aesthetics, see if we can get. They're really small though. Teeny tiny. There we go. Okay, so there we go. Crystals are on. Now I think, actually let's clean up, I'm gonna clean up this mess a little bit because we're gonna be soldering SIM sockets now. Finally. We're just cleaning up here. rid of this ugly residue. So it always looks better when it's wet with IPA, but then when it dries, the residue often comes back. All right. So going back in our little baggie here. Now, I think in order to do the chime test, we need 4 SIM sockets. We need the ROM SIM sockets down here. We need all the IC sockets. Oh, actually, before we should solder on the caps, the big axial caps. Right, let's do that first. Axial caps. Here they are. Got 2 of them lined up there. So for aesthetic reasons, I believe these are Vichy caps. Yes, Vichy. These are Vichy brand, and I kind of like the aesthetics of these. They're fairly pricey, kind of expensive caps, but I think it'll look good. So we should also, I think I want to align it so we get these nice little polarity stripes on top, like so, like a little ridge. So this is fairly easy. The big cap goes on C2 here, and the smaller cap goes on C11. The big one is 470 microfarads, 25 volts. I think originally it's rated for 16 maybe. And this is 220 microfarads, 16 volts. Yeah. So this is a bit overrated. You like the microfarad and voltage on top? There's Vichy. Like so. Well, they're still on the side there. You can see them like that. I'm gonna do with my approach. Gonna. Oh, I think to get nice bends, I'm gonna use my pliers. But this is a good angle. Get a nice bend on there. Oh yeah. Well, interesting. Yeah. I think it's kind of retro. I don't mind this. It's like retro bitmap font. So let's see here. The silk screen says plus right there. So the minus indicator should go down, I believe. Like so. I believe this is correct. Oh. Bend these over. There it is. Since the legs are pretty long, let's just solder one at a time. Here we go. Wire cutter, these things. Flush cutter. There we go. Do the other cap down here. And I'm gonna do the same thing with the polarity on top. I'm kind of just lining this up like so. So I guess this is where this setup with this microscope is not the best, because now we're doing through-hole soldering. It's going to be hard to get a good view. All right. Anyways, we have our two big caps attached there. That's progress. All right. Back to the box. So what we have is one 64-pin SIM socket from Phoenix Enterprises, I believe it is. So that's one thing we need. Let's see if I can find the... Oh, there you go. And here are the 30-pin SIM sockets, also from Phoenix Enterprises. I think that should be a good start. So yeah, now we, as I mentioned, I'm going to populate the 4 lower SIM sockets first. So that we have some leeway to work on the FPU if needed. Let's get 4 of these out here. Okay, so I think, let's see here. It seems what the silk screen indicates is that the latches should be facing this side, if I'm not mistaken, like so. Let's compare with the So yeah, that's also what's happening here, right? The latches are facing inwards. I'm also happy to report that. Don't you still have them on the journal board? Yes, yes, yes. They are right on here. That's what I just showed. So yeah. And luckily, I think this is Bolly has updated these Gerbers so that the little plastic pins here that stabilize the SIM sockets actually line up with the holes in the PCB. That's actually a huge, huge help. I've had to trim those in the past for other jobs, and it's a pain. That's interesting. So actually, there's a delay, huh? Yeah, I thought that maybe you didn't pay attention at that particular moment and missed that. I think I'm gonna the the microscope doesn't really help now. Maybe put the camera like down here. I wonder if we can get like an angle, different angle. I don't know if this is more interesting. Ideally, I should have like a stand here that could zoom in on, or give a better angle of this part. So anyway, so what I like to do with these SIM sockets is you start out by soldering one edge, like so. So one pin is in. Gonna focus on the wick label, okay? And the ruler. Yeah, you're right. The camera is very confused about what to do. Yeah, maybe this is not a good idea. So maybe I can just pull this away to the side, like so. I was good? Okay. Yeah, I'm not really set up well for... Okay. I'm not set up well for through-hole work. So anyway, I like to solder one of these pins and then kind of make sure that this is flush before I start soldering the others. So I actually from up here the focus on the board is bad. Okay. Yeah. And once we know that the socket is nicely flush against the board, we can just do a little bit of drag soldering. You should work. Let's see how well it works here. You know, just drag it all down while applying solder. Maybe for the... No, wait, never mind. Right. Oh, actually there are two. I didn't get solder in the first two. Here we go. Okay, I think those joints look all right. So let's pull the blue tack. The one drawback with blue tack is that if the component gets too hot, it may start melting, which is never fun. So do the next one. Put the blue tack on there. Put solder in one hole, one end there, and then kind of make sure that, yes, it's very nicely flushed on there. And then we go down the line. Drag soldering. With this technique, it's important not to go too quickly. Make sure that the soldering iron has enough time to get heat into all of the holes. So keep dragging slowly and adding solder. I think those joints look very good. Next sim socket. Put the blue tack on like so. Solder one pin. Actually, I noticed it's not, Right, so one lesson learned is this blue tack is not holding on to the sockets quite as well as it should when we're doing the drag soldering. So what happened here is that the second SIM slot is not perfectly flush there at the end. And it's a bit too late to do anything about that. Not the end of the world, but it's not perfect. So I think what you want to do in these cases is you do one end, make sure it's flush, do the other end, make sure it's flush, and then you do the middle ones. So let's add solder to the other end, and then we'll push on the socket with our finger, applying heat. Very nice. Okay, now we can do all the other pins. All right, let's get rid of the excess solder there. Fourth SIM socket. Still not melting, that's good. There we go. Fourth SIM socket seems to be on there all right. Solder one edge, like so. Make sure it's flush. Seems good. Then we do the other side. Make sure it's flush. Yep. Beautiful. So again, what I'm doing is I'm applying, when I start on one of these, I apply solder on one of the edge pins. I then push down on the socket while applying, kind of pushing down with my finger, and then letting the solder cool a little bit, so that I have a flush socket on one end, and then I do that on the other far end pin. Okay, rid of excess solder. Beautiful. So we have 4 SIM sockets, which is well enough to do a chime test. But yeah, the SE30 requires 30-pin RAM SIMs to be installed in groups of 4, sets of 4 with the same value. So we need 4 sockets to boot the computer. Yeah, and 4 RAM sticks in there. All right. So next, let's solder there we go. The ROM SIM. So there are 2 ways to get a ROM onto this reloaded board. One is the traditional ROM SIM socket, which is what was in an actual SE30. The other one is these 4 ROM chip sockets, and I believe these are of that what's it called again? PLCC types. So you can install 4 PLCC sockets and install those 4 RAM chips. I think I have the socket that I have is set up like that. Oh, sorry, the ROM SIM I have. But anyway, I'm going to use the SIM. So I have this SIM socket for that. Oops, shouldn't drop it. So yeah, good question. So I'm using a Maxim. Let's see here, if I can show it off. Here we go. So this is what I went with. So this is not the what's it called again? The big mess of wire thing. This is a Maxim, which is sort of the simpler version, put together by GG Labs. So this is effectively a hacked 2SI ROM. So yeah, Rominator. Thank you. So this is not the Rominator. So yeah, it's a hacked 2SI ROM that takes away some checksum checks and RAM checks. Otherwise, it's just a 32-bit clean ROM for these computers. It doesn't have any fancy stuff like the hacked Happy Mac boot logo or the modified startup sound chime or the ROM disk. So I don't really care about that stuff. I know, Brandon, you like the ROM disk feature functionality, but I feel like I have so many ways to boot a Mac, so I don't necessarily need that. Maybe I'll regret that, but we'll see. Anyways, let's install this sim socket. Where did my blue tack go? There's my blue tack. Right, you're right. It doesn't support probably smart port booting either. I have plenty of Macs that do that, so didn't really feel the need to do that for SE30. Yeah, the original ROM sim was in really bad shape. Okay, so let's solder actually these two edge pins on this one. This is a more high density ROM socket or sim socket. And then let's do the push down while heating both of those. That seems okay. Then to the other side. Oops, not enough solder. Like so. And then see if we can do the push again, so we heat both of those while pushing up. I think that's nice and flush. Seems good. Solder all of these pins. Maybe let's bring the microscope back and see if we can get some shots of doing this. Let's bring this up a little bit. Oops. There's something, I think this tip is pretty worn, so I keep getting sort of too much. You see, it's kind of worn on the side there. I think that's what's happening. So a lot of solder kind of gets on. You can see this soldering, this tip is leaving a lot of residue like that when doing the drag technique. And I think if you had a fresher tip, you would not have that problem. This is now very well used. We need more solder here. Oops. All right. To the other side, bring the microscope over here. Oops, a bit too out of the shot there. But I'm coming down to you. Mm, okay. All right. So, we've gotten to a pretty decent state now. Let's bring this camera up. There we have it. We're now fairly close to a machine that can work. Maybe. We still need to get the IC sockets here, the CPU sockets. Need these IC sockets, IC sockets, IC sockets, and then this interconnection header that hooks this machine up to the mother and to the analog board, and then we can test it. So I think I'm gonna call it a wrap there. It's time for dinner. So yeah, thanks for watching, and Brandon, thanks for supporting and helping out. See you all next time. Bye bye.